Welcome to the series playlist on Catalyst University. My name is Kevin Tokoph. Please make sure to like this video and subscribe to the channel for future videos and notifications. So as you could probably obviously tell, this entire playlist is going to be dedicated to series, and then eventually we're going to go into power series, which is a special type of series that's very important. Now, before we ever do series, there's a few things that you need to kind of have in your memory and at least be able to do to some extent if you want to be successful with doing series problems. You need a little bit of integration skills. There's some problems that we'll see that actually use integration. Mainly the thing to remember is improper integrals. Although you might see a few use substitutions, and we're going to have a ton of L'Hopital's rule, particularly with the improper integrals that we'll see in one of the evaluation tests. Also, we're going to have a lot of limits to evaluate. So one of the things that's going to crop up a lot is L'Hopital's rule, again, when we're evaluating just regular limits that don't even involve an integral. And then the vast majority of this is really just messy algebra. So I want to answer a question. What in the heck are series used for? Well, I think series in general are actually the most underappreciated and most poorly understood aspect of all of calculus. You start off with differential calculus, where you have all these derivative and differentiation techniques, power rule, product rule, chain rule, quotient rule, all these special derivatives like exponential, log functions. You even get into partial derivatives later on, which you probably haven't done at this point. But derivatives are still very important. They calculate rates of change. They're used in physics. For example, if we differentiate position with respect to time, that gives us velocity. If we differentiate velocity with respect to time, it'll give us acceleration. And there's countless more examples of very important differentiation type of problems you can see in physics and chemistry, etc. So rates of change, okay? So that's why derivatives are important. I don't think I need to convince you there. When you got to integrals and integration techniques, we saw use substitution, integration by parts, trigonometric integrals, trig sub, the feared trig sub, even partial fraction, decomposition, improper integrals, and eventually you'll get to double and triple integrals when you do multivariable calculus. I don't think I need to convince you why integrals are important. You can calculate the area under a curve. And in some courses like thermodynamics, physical chemistry, etc., that you find in engineering and chemistry majors, you can calculate the work done by, say, the expansion or compression of a gas. It turns out that the work is equal to the integral from volume 1 to volume 2 of the pressure integrated over differential volume. Here's actually a graph of that. And if you actually know a formula for pressure, you can actually do this integral and calculate the maximum amount of work done. Again, countless more examples of integrals that you'll come across in all types of physics and chemistry. But the question is series. So we have all these derivative techniques, we have all these integration techniques, and we're going to find we've got all these series, what are called series convergence techniques. They are tests to determine whether or not a series converges or diverges, which we'll discuss in a minute. We have a p-series test, a geometric series test, two comparison tests, integral test, alternating series test, ratio, root test, all this stuff. And you're going to go through these and be like, what the heck are they used for? Well, here's what they're used for. Evaluating a power series. Power series may not mean a lot to you right now. In fact, we won't cover them for a while. It'll be the very end of the series playlist. But it turns out that almost every single function that you see on your graphing calculator, exponential functions, logarithmic functions, trigonometric functions, your calculator does not interpret e to the x as e to the x. It's really hard, actually, for a calculator to do that. Instead, it turns out it's much easier to express e to the x as a power series. It turns out any function that you have dealt with in any of your previous courses in calculus can be expressed as a power series, an infinite power series. And calculators and computers are much better at dealing with power series than they are at, for example, directly coming at logarithm base 10 of 5. It's really hard for a calculator to do that directly. It doesn't even do it that way. There would be a power series representation for log or exponential or cosine, sine, etc. Okay? And even other things like some integrals such as the Gaussian integral, which is actually determining the area under a curve for the normal distribution or bell curve that you would see in a statistics course, that integral is virtually impossible to do with the integration techniques that you saw in the previous chapters in your textbook. It turns out that the Gaussian integral is much easier to integrate if you actually convert its function to a power series and then integrate the power series. In fact, that's actually how programs do it. They run the bell curve equation, or the Gaussian curve equation, as a power series. So there's a lot of sort of behind-the-scenes aspects of series that you don't directly see, but they're used all the time. You probably use power series every day without even realizing it. And these series convergence tests or techniques are used to evaluate the power series. Okay? So again, very important, but more from an indirect kind of a background perspective. Okay? Now, let's go over some very basic stuff about series. These first two series I have here are what are called finite series. So let's talk about series notation first. Series are represented by this capital Greek letter sigma. Okay? You'll have a sort of a variable down here. It's usually an n or a k, although the vast majority of times it's an n. This is called your indexing variable, your index. It'll say n equals some number. Whatever number is, that's your first term of the series. In this case, my first term is 1. Okay? And I'm just going to evaluate a sub n at n equals 1, and then I'm going to add on a evaluated at 2, and then add to that a evaluated at 3, and then add to that a evaluated at 4. Why don't I go any further than that? Because the top number at here tells me what term to stop at. So I should be adding actually 4 different terms together. A 1 term, a 2 term, a 3 term, and a 4 term. And by the way, this n does not have to start at 1. It could start at 0, it could even start at 5. But this top number tells you what number to go up to. Let's look at an example of that, where we have an explicit a sub n. Here's the series from n equals 1 to 4 of 1 over n squared. So how would we actually evaluate this? Well, we can get an exact answer for this. Our first term is 1, so 1 over 1 squared is 1 over 1, right? So this is actually my a sub 1 term. Whoops. My second term would be with n equals 2. So 1 over 2 squared is 1 over 4. This 1 over 4 is my a sub 2 term. N equals 3 is the next, so 1 over 3 squared is 1 over 9, plus 1 over 4 squared is 1 over 16. All right? And since I'm only going up to 4, I'm just adding these terms together. Okay? And with these finite series, you should be able to get an exact value of the series if you spend enough time with it. We can get common denominators here, add them all up, and this series actually, when you add these numbers together, gives you exactly 205 divided by 144, whatever that turns out to be as a decimal. These two are finite series because the number that you actually go up to, the highest number, is a finite number. These two at the bottom are what are called infinite series, and they have some different and unique properties from finite series. So an infinite series is one where, again, the index can be any number, but the top number up here is just infinity, meaning the number of terms you're adding together are infinite. Now that being said, because you're adding an infinite number of terms, you can't evaluate these series, okay, by just adding up a number of terms. We can determine whether or not they converge or diverge using calculations and tests from Calculus 2, but beyond that, to actually evaluate these, you need much more advanced math. So we're not really going to be evaluating these for the most part, okay? But here we have the series from n equals 1 to infinity of a sub n. So you'd have an infinite number of these a terms added together, okay? Let's look at an example where I certainly won't show an infinite number of terms. Series from n equals 1 to infinity of 1 over n squared. Well, I'm going to have 1 over 1 plus 1 over 4 plus 1 over 9 plus 1 over 16, 1 over 25, 1 over 36, 1 over 49, and so on and so forth. And you're going to add an infinite number of these terms, okay? Now, to preface where we're going next, if I add up an infinite number of terms, even though I'm adding an infinite number of them, two things could happen. One, the sum of every one of these infinite number of numbers could actually turn out to be a finite number, which it does many times, or it could blow up to infinity and not even have a sum. It would just diverge to infinity. And we've talked about divergence when we did improper integrals. Now let's talk about some of the most important properties and results of series convergence tests. And that's whether or not a series converges or diverges. All right, so let's start with this first series up here. We have a series from n equals 1 to infinity of 3n. Now let's look at the first few terms of the series. We'd have starting at n equals 1, 3 times 1 is 3, plus 3 times 2, which is 6, plus 3 times 3, which is 9, plus 12, plus 15, and so on and so forth. So we're adding bigger and bigger numbers, and we're adding an infinite number of them. I don't think you really need any series evaluation techniques to know that this goes to infinity. All you really need is some logic and some reasoning, but this should blow up to infinity. And if you have a series whose sum goes to infinity, that means it diverges. Or vice versa, if you determine the series diverges, that sometimes means that the sum just goes up and blows up to infinity. Okay? Now, here's another series down here which may not be so obvious. The series from n equals 1 to infinity of the quantity 1/2 raised to the n power. We'll see later that this is actually a geometric series, and it's a convergent geometric series. Let's look at the first few terms of the series beginning at n equals 1. We have 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1 over 32 plus so on and so forth. And this is one of the few types of series, such as a geometric series, where you can actually determine its exact value. Most you can't, unless you have very, very complicated math, which you won't actually do in this course. But this geometric series, it turns out, is equal to exactly 1. Meaning if you add up an infinite number of these terms, infinite number, it actually settles on a finite number, that is 1. And because it doesn't blow up to infinity, but it settles on a single value, we say that this series, this geometric series, converges. Okay? And usually these are the series that are actually useful to work with when they converge. Okay? And in general, finite value, when it settles on that, the series converges. When it blows up to infinity, that means it diverges, and vice versa. But there's one other option for when a series diverges. And that's when you have a series that doesn't actually have a predictable sum, or it has no sum, which means typically it oscillates between either a positive and a negative number, or like a negative number and 0, or something like that. And here's a great example of that. Here we have the series from n equals 1 to infinity of -1 to the n power. All right, let's think about what the terms would be, starting at n equals 1. -1 to the first power is -1. n equals 2. -1 squared is +1. n equals 3, or -1 cubed, is -1. And so you can see that each term is going to oscillate between positive and -1. -1 plus 1, -1 plus 1, -1, and so on and so forth. Here's a little notation here, a partial sum. So if we look just after the first term, the sum, -1, is just -1. But if we add a 1 to that, it becomes 0. Then we subtract 1, it goes back to -1. Then add 1, it goes to 0. And then subtract 1, it goes back to -1. So this sum of this series, even though it goes to infinity, it'll never rest on a single value. This series, apparently, its sum alternates between -1 and 0 an infinite number of times, and it never settles on a single value. Therefore, this series has no sum, and is also divergent as well as a result. So it diverges. Okay? So the keys here, if it settles on a single value, and it's finite, it converges. If it blows up to infinity or never settles on a single value, in which case has no sum, it diverges. Okay? And one more thing about infinite series. All right, when we talk about series in the context of calculus, it's assumed that we're talking about infinite series unless stated otherwise. So I'll usually just say series, okay? But you're to assume that I'm talking about infinite series. We're not really going to come across finite series because in this context they're really not useful for calculus. All right, let's assume that the series of a sub n and this series of b sub n both converge. Okay? Assuming that both a sub n and b sub n converge, if we add these two series together separately, it's the same as the series from n equals 1 to infinity of a sub n plus b sub n. So if we took the argument from both of these series, a sub n and b sub n, and added them together and then summed that from n equals 1 to infinity, these would be the same. But that's only assuming a sub n and b sub n both converge. If one of these diverged, say b sub n diverged, then the whole thing would automatically diverge because, let's think about it, what's a finite number plus infinity? Well, it's just infinity. So both of these have to converge for this statement to be true. And along the same lines, we have a subtraction version of this. The sum from n equals 1 to infinity of a sub n minus the sum from n equals 1 to infinity of b sub n is the same as the combined difference of the series from n equals 1 to infinity of a sub n minus b sub n. Okay? Very important. But one of the most important ones that we'll actually see later on, particularly with things like the power series, radius of convergence, and so forth, is, let's say you have the series from n equals 0 to infinity of c, some constant number, like a 5 down here, times a sub n. Well, it turns out that any constant number you can pull out in front of the series. So this is the same as c times the series from n equals 0 to infinity of a sub n, assuming a sub n converges. Okay? And an example of how this works would be if you had 5 times the series from n equals 1 to infinity of 1 over n squared. And again, I can throw that 5 back inside the series. And so what would happen is I would just literally multiply a 5 by every single term in the series. If you just look at the 1 over n squared, which is what we saw in one of the previous slides right here, you end up with 1 over 1 plus 1 over 4 plus 1 over 9 plus 1 over 16 and so on and so forth. But if I pull this 5 back in here and distribute it to each term, I end up with 5 plus 5 over 4 plus 5 over 9 plus 5 over 16 and so on and so forth. Okay? Now, it turns out there's other rules for multiplying and dividing series. They're more complicated, and we really won't see any of those when we're dealing with series in the context of calculus. These are really the most important series properties that you can understand for the purpose of this course, and to understand what the meaning of converging and diverging is with respect to infinite series. All right, so now that we've covered some bare basics of series, infinite series that is, we can now get into some series tests. All right, so hopefully this gave you some good information. Please make sure to like this video and subscribe to the channel for future videos and notifications. Thank you.